Welcome everyone. As you all start joining, we're going to give everybody about a minute to join us. We'll get started. Thank you to everyone who's joined so far. We're going to get started in about 30 seconds here. All right, welcome everyone, and thank you for joining us today. This webinar will be a panel discussion on the recently released report from APS and Optica entitled Monitoring Methane Emissions in Oil and Gas Operations. I am Michelle Bailey. I'm a researcher at the National Institute of Standards and Technology in Gaithersburg, Maryland. I'm a contributing technical author to this report, and I will be the moderator for today's event. We will start out by going around the virtual table here to learn about the motivations, findings, and recommendations of the report before we wrap up with a Q&A session. I do want to note that the chat box will be open for conversations amongst participants, but please be sure to submit any questions that you have for our panelists through the Q&A feature. We will do our best to get to as many of those questions today as possible. So without further ado, I'd like to start off by asking each of our panelists to briefly introduce themselves. Bill, would you like to start us off, please?
Sure, thank you. I'm Bill Collins. I'm the past chair of the APS panel on public affairs that launched this report. I also serve as a division director for climate and ecological sciences at Lawrence Berkeley National Laboratory, and I'm a professor in earth and planetary science at the University of California, Berkeley. Thank you, Michelle.
Thanks. And Ray, would you like to introduce yourself?
Yes, I'm Ray Orbach. I was on the panel on public affairs and chaired the Energy and Environmental Subcommittee, which began this report. And I'd like to thank the American Physical Society for all of the help that it has given to our panel and to producing this report. I'm a professor at the University of Texas at Austin, having appointments in mechanical engineering, physics, and the geosciences.
Thank you so much, Ray. And Ian. You're muted.
Sorry. Yeah, my name is Ian Coddington. I'm a scientist here at the National Institute of Standards and Technology here in Boulder. I co-author on the report as well, and my background is generally in developing sensors for greenhouse gas sensing.
Perfect. Thanks so much. So let's jump in now to the motivation of the report. Ray, could you share a bit about how this study came to be?
Well, thank you, Michelle. When the panel on public affairs looked at the effect of methane in the atmosphere with regard to increasing the temperature of the surface of the Earth, it ran across some troubling observations. First of all, it accounts for roughly 30% of the global warming since pre-industrial times. So it's a major contributor to our global warming issue. In fact, because it lasts only about 12 years, if you look at it over a 100-year period, it's about 30 times as potent a greenhouse gas as CO2 is. When you look at its source, about half of the methane that goes into the atmosphere is anthropogenic in origin. That is, it comes from our behavior as a civilization. Roughly, oil and gas production, distribution, and treatment account for about 30% of the methane that's in the atmosphere, whereas agriculture and waste typically picks up the other 2/3, with a small amount coming from biomass and biofuel combustion. What is important is that the methane increases roughly at 0.5% per year, and it stems from roughly, again, about half of that increase over the last decade comes from oil and gas. And so we chose to look at the oil and gas issue, seeing if we could figure out how to encapsulate it and then how to deal with it. What we found was that a relatively small number of emitters, 1 to 10%, actually contribute more than half of the methane emissions from the oil and gas sector. The advantage of focusing on oil and gas as a major component is that it tends to be point sources, whereas when you look at other sources, they tend to be distributed. So it may be possible to deal with these point sources on a much more effective scale. Why should the American Physical Society and Optica be involved? Well, the sensors of methane emitters require inexpensive and unique characters. Optica and APS can develop sensors for remote sensing and in situ measurements of different carbon isotopes. They can create and support high-resolution spectroscopic databases. And they're also involved in the creation of high quantum efficiency photodetectors, which can bring together satellite, airborne, and ground-based observations in a cost-effective fashion. So these two societies then have the intellectual capability of dealing with one of the major aspects of controlling methane emissions. And why now? Well, the next 2 decades will be crucial if we are to meet the 2 degree Celsius warming by the end of this century. And in fact, the more ambitious 1.5 degrees target for 2100 requires that, excuse me, a 2% reduction per year in methane concentration takes place. You need to put that against the fact that the methane concentration is increasing at about 0.5% per year. The good news is that methane only lasts for about 12 years in the atmosphere. And so if we are capable of actually controlling it and reducing it, we will see the effects within the next few decades. Whereas when you look at CO2, you're talking about millennium timescales. So it's really important that we focus, in our view, on methane in these next 2 decades and try and reduce the amount going into the atmosphere.
Thank you so much for that background, Ray. So to build on the need to monitor these emissions, Bill, perhaps you can talk about where we stand now in terms of understanding our current methane emissions and sources. And I will bring up some slides for that.
Thank you, Michelle. So the context, as Ray mentioned, is that there's now impetus emerging from both the 26th Council of the Parties that occurred in November last year, in Glasgow, and also President Biden's plans around methane that emerged from COP26 to think about monitoring methane and regulating it more actively. And in order to do so, if we're going to set a baseline against which to measure the efficacy of measures going forward for reducing methane, we need accurate inventories now to determine if methane emissions have decreased. And of course, as Ray alluded to, these inventories already exist in some form. The Environmental Protection Agency, for example, produces annual inventories of emissions by source. And the challenge for the regulatory agencies is the sourcing of this information. Now, one thing that we know at the moment is that these inventories, due to no fault of the regulatory agencies, have tended to underestimate emissions. And so one of the issues that we call out in the report is the need for much more accurate baselines against which to measure policy. And if we could go to the next slide, Michelle. Thank you. So unfortunately, there are pretty severe disparities between methane inventories and measured emissions. And the disparities all tend to go one way. The inventories are low relative to reality. So multiple studies have identified significant underestimation of methane emissions. And this is true both for the California Air Resources Board, and I'm showing some graphics comparing tower data to their emissions inventories, as well as to emission inventories from the Environmental Protection Agency. And again, this is despite the best efforts of these agencies and a lot of really hard work by their staffs. But we clearly indicate, based on the peer-reviewed literature, that these inventories are, at the moment, insufficient for accurate baselining of regulatory policies going forward. And so what we call for is creating a panoptic observing system. It consists of sensors in the ground, in the air, and in space to really try to nail down emissions across the United States and globally. Next slide. As one of the issues that Ray mentioned, it's a fortunate feature of the oil and natural gas industry, is that this is not a question of literally eliminating every leak. Methane emissions in oil and natural gas operations are dominated by a small number of what are known as super emitters. And Ian is going to describe this graphic in greater detail, so I won't, but just to mention here that these super emitters are the majority of methane emissions in important oil and natural gas production regions. And in fact, if you just target leaks of greater than about 30 kilograms per hour, you will reduce emissions from oil and natural gas by somewhere between 70 to 90%. And that's a very fortunate feature of this fat tail distribution of emissions. It means that a little will go a long way, and it's an actionable and achievable level for industry. And with this, let me now turn the floor back over to you, Michelle, for the next steps in this briefing.
Thank you, Bill. So with these unique challenges that this emissions monitoring presents, Ian, can you share a bit about our current measurement capabilities and maybe how they compare to our measurement needs?
Yes, absolutely. If you advance the slide, thank you. So this is actually a very exciting time in terms of measurement capability. There's been a lot of new sensors and techniques that have come online, partly because of investment from RP and Department of Energy, and even the oil companies themselves, and a number of others. And it's actually kind of a optimistic time. It looks like there's a route to kind of solve this problem. But first, I want to start by talking about this plot that Bill just showed up. And apologies for the redundancy, but honestly, if there's one thing to take away from this report, it's actually captured in this plot. And this is essentially what Bill is saying, that what it looks like the leaks that matter are the big ones. This is essentially the conglomeration of a number of studies from across the US, where they essentially looked at all the leaks in thousands of measurements and categorized them by leak size, and then integrating them up, starting with the largest leaks first, look at what, how much of given leak size contributes to the total emissions. And what you see actually is that the very large leaks are responsible for maybe even half of the emissions, and even moderate large leaks get you to about 90% of the emissions. And in industry, actually, increasingly there's this 90-10 rule, which is saying that roughly, this is not exact at all, but roughly maybe about 10% of your leaks are contributing to 90% of your problem. So from a standpoint of mitigating this issue, it's fantastic news, because it means, one, we can identify these leaks and focus on these leaks, but also there's a rare alignment. Those 10% of the leaks, or 10-ish% of the leaks, are really the ones doing environmental damage, but they're also the ones that are costing oil companies revenue. These are big leaks that are absolutely worth fixing. And the name of the game is, we want to be able to identify these leaks quickly. We want to be able to quantify them, and we want oil companies to have the ability to direct resources to those leaks quickly to mitigate the issue. So we actually are, from a sensor standpoint, in an interesting situation where sensitivity is not really the issue. Ground-based and terrestrial-based airborne all have plenty of sensitivity to see these large leaks. Satellites looking from 100 kilometers away, it's a little bit more of a struggle, but they still actually can see an awful lot of the important emissions. If you advance the slide, Michelle. So what does matter? Well, one thing that's really exciting about this new technology, and actually has existed to some degree before, but is we need to be able to quantify these leaks. We need to be able to target resources, or let the companies target resources quickly. Also, continuous monitoring appears to be quite important, right? You want to catch these leaks quickly. So you want low latency, but also the one piece of the puzzle that's maybe not well understood is intermittency. These leaks, they're complicated systems. It looks like a lot of these leaks do sort of toggle on and off. You want to be able to understand that behavior. You want to be able to get a work crew to that site before the leaks go away. And then after that, what really matters is cost, and that's where the things have improved. And basically, we want to get the cost of the sensing low enough that it is financially viable for oil companies to adopt these technologies. And what that means, in addition to the sensor cost, of course, being low, you want full or partial autonomy in your sensor. You want low false positives. You want to be able to locate the leaks reasonably well, so work crews can identify the leaks quickly. And also, you need to be able to integrate into the oil patch workflow. That's at the end of the day, oil companies have to be the ones to repair these leaks. So if you can advance the slides, Michelle. So we tried to summarize what we saw in the technology, or what's available to address this problem, and we broke it up into kind of 3 categories. And the nice thing is, or the bottom line is it looks like there's some great technology out there. Generally speaking, there's a lot of ground-based technologies, which are frankly a little bit newer. They tend to be very autonomous. They have a lot of the things you're looking for. They can be near real time, excellent sensitivity, and they can a lot of times locate the leaks fairly precisely. And continuous observations are actually often possible with these guys. Maybe not completely continuous, but certainly daily or sometimes hourly is completely doable. And what's particularly exciting is there's a lot of flavors of this technology, but they all work in kind of the same way, in that they measure concentration in wind fields, and they use the meteorological model and the concentrations to sort of back out the leak rate. But beyond that, there's very few similarities. They diverge wildly. But it seems like a very interesting way going forward, or interesting approach going forward. The only real downside is you have to instrument every well, so there's power and communication logistical problems. There's over 1 million wells out there, but it's so they take a little while to scale up. But these are an attractive way to address the problem. If you advance, Michelle. The other approach that's where there's a lot of really interesting activity is airborne. Airborne measurements are responsible for a lot of our understanding right now of oil and gas leaks. They can be, they can have all the sensitivity that you would require. They can actually, in some cases, localize leaks. Particularly these newer LiDAR technologies can give you sort of meter level resolution on the leak, which is extremely helpful for ground crews. And seems to be there's multiple commercial options at this point too. There's a lot of companies that are actually marketing directly to the oil and gas infrastructure. And the other thing that's really nice about this technique is that it's quite flexible. If you need to measure 1,000 wells in California and a week later do the same thing in North Dakota, that's completely doable. The downside of or the limitation, I think, of aircraft measurements at this point that we identified is, one, they're not autonomous yet. You are always paying for a pilot. To be autonomous would require some sort of unmanned aerial system, and the regulations and other concerns are still there for that approach. And the other issue is that they are a single snapshot in time. They are only seen do a quick pass over a given well, and then they're on to the next well. So the intermittency might be an issue for these ones. Next slide. And the last system that we tried to characterize in the report, or to summarize in the report, were the satellites. Satellites are fantastic in that they really also provide a global picture. And of course, methane is a global problem. We're going to need to understand not just what's going on within the US, but outside. They do appear to have sensitivity. Certainly see super emitters and maybe as much as 50 or 60% of all emissions from oil and gas infrastructure. And there's both private sector and government options. This is also an interesting space in that it really is quite growing, or is growing. The downside with satellites, of course, is there's a little bit of a limitation in sensitivity, but also their field of view is a little bit constricted. You might have to stitch together different data sets from multiple satellites to really get the full picture. And then again, they are a single snapshot in time. The revisit times are not that frequent. And also there is some expense associated with satellites. But in terms of understanding the international picture, it's probably our best option. If you skip forward one more, so I think in summary, the takeaway from this report is that monitoring systems, the key in designing new ones is they need to be rapid, and they need to quantify leaks, or they need to find these leaks quickly. What's particularly interesting right now, though, is it does appear that there's a lot of measurement options that actually meet industry needs, and actually their costs seem to be low enough that they're seeing large-scale industry uptake, which is very exciting from the standpoint of dealing with this issue. Greater scale is needed. At this point, only a small number of wells are monitored. Or at least continuously, and finally, that's a factor. The fact that we've only begun to understand this problem and the cost benefits of monitoring. But anything we can do to increase scale is going to be very helpful for going forward. Lastly, there's still this question of intermittency, but there's this Project Astra and others that hopefully we'll get some better data on and understand that problem and how that feeds into sensor technology. And lastly, this is exciting because the technologies do seem like they will feed into other monitoring, methane monitoring approaches well beyond the oil and gas infrastructure. And with that, I'll turn it back to you, Michelle.
Thanks so much for that overview, Ian. Bill, if I can turn back to you now, what are some of the technological challenges that we're facing, and what are the research needs that we need to better evaluate methane emissions in this particular sector?
Sure, thank you, Michelle. Coming back to the point that Ray raised, there is plenty of room for research by the physics and optics communities to improve our monitoring of methane and other greenhouse gases. And I'm going to mention three that we discussed in the report. The first is improved understanding of the spectroscopy of methane. What spectroscopy alludes to are the ways in which methane can absorb both sunlight and infrared radiation. And for the purposes of remote sensing that we've just been discussing, remote sensing from a distance, looking at methane sources, it's the near infrared light, it's solar radiation that's invisible to the naked eye that's particularly important. So our understanding of the spectroscopy of methane has come largely from the laboratory, as well as from studying the outer planets in the solar system, which have 1,000 times as much methane as Earth. These spectroscopic databases are used to inform the ways in which we interpret measurements from laser instruments that I'll come back to in a moment, as well as from satellites. And we know from experience with, for example, the EU's TROPOMI instrument, which is an instrument dedicated to looking at methane, that the uncertainty in methane spectroscopy is affecting our ability to accurately retrieve methane burns in the atmosphere. And this graphic on the right illustrates the fact that we know a portion of the spectrum of methane from laboratory measurements, but the majority of the spectrum, because the methane absorbs clear up to the violet wavelengths from the sun, is only known by studying the outer planets. And so there's a lot of room there for improvement of our understanding of how methane absorbs sunlight, and then folding that information into our ability to sense its presence in our environment. Next slide. A couple of other, one other type of measurement, there would be two other kinds of measurements that would be extremely useful or helpful for attributing the sources of methane. So this is a little bit like a detective game, right? You detect methane in the environment, and the question then is, did it come from biogenic sources that Ray alluded to in his introduction, or from oil and natural gas? And there are a couple of ways of doing that. One of them is by looking at the isotopic composition of methane. So this is how heavy the methane is by adding neutrons basically to the atomic nuclei. And as it turns out, biogenic methane is typically depleted in these isotopes relative to fossil fuels. This is illustrated in this graphic on the right. So if you look for depletion levels, that allows you to figure out, am I looking at a source that's likely, am I looking at methane that's likely from a biogenic source, say a landfill, or from a leak from an oil and natural gas field? And the other clue in this detective game is ethane. So ethane is emitted from fossil fuel derived methane, but typically not from many biological species and sources. Unfortunately, both of these sensing isotopes and sensing methane is a very challenging measurement problem. And so this is another place where the research community or communities in APS and Optica could work with those of us who are trying to sense methane and really improve the ability to sense these trace species in the Earth's atmosphere. So more room for research. Last slide, Michelle. The last topic I'll mention that's an area where additional research would be most welcome, and I can see Microsoft has done its usual number with Greek symbols here, my apologies. So as I mentioned earlier, we need to measure methane's effect on, we can measure methane's effect by looking at its absorption of sunlight. And the wavelength here, this is a wavelength that's in the, again, in the near infrared, a portion of the solar spectrum where our eyes are not particularly sensitive. It turns out it's a really challenging place to make measurements because the Earth's atmosphere doesn't scatter that much sunlight back to sensors. For example, a satellite instrument that's shown here in cartoon form on the right, which is staring down from space. And so we need to greatly improve the quantum efficiency of these sensors to get them up to close to 1, get them so that these sensors respond very quickly to any photons that are scattered back from the Earth's atmosphere, get them to work effectively under daytime conditions. And so there's, again, room here for both the American Physical Society and for Optica to, and scientists working in both of those societies to help us really crack open this problem of sensing methane from a distance and to be able to profile it from space, which would be completely game-changing. With that, let me turn the floor back over to you, Michelle.
Thanks so much, Bill. So I'm going to stop sharing my screen here. So in addition to the research advances that Bill just identified, Ray, can you comment on some of the policy recommendations that are outlined in this report?
Thank you, Michelle. There are 3 areas that the policy and policy gaps focused on. The first is detection. As you've just heard, we really need 24/7 continuous monitoring of methane emissions. So much of it tends to be episodic, especially the large producers. We need to work with the state and the private sectors to quantify methane emissions from oil and gas production, transmission, and processing sites. We need to develop new methane sensing technologies. And it should be a goal of the federal agencies, EPA, NOAA, NIST, DOE, and NASA, to begin to develop integrated programs for these developments. This would include proof of principle instrument research, as well as development of working prototypes that could be scaled to field operation. And finally, there needs to be a national facility or facilities for testing and intercalibration of methane measurements, a national test bed for methane sensors, especially space-based monitors that work in different frequencies and are on different platforms, need to be brought together and made coincident with one another in terms of sensitivity. The second area is data and models. We need a unified repository of methane observations that's available to the international climate community. It would be a repository of methane observations, products, inventories, and geographic information systems. It would lead, hopefully, to a national methane model. It would close gaps in our current observational networks. The current inventories, as you heard Bill describe, are often dated on outmoded methods of calculations, and they should be updated by the current state of the science. And finally, the development of a national methane hindcast and forecast modeling facility that, for example, NASA and NOAA could develop. This would enable the projection of benefits of specific emission mitigation. It would also help to check the consistency of improved emissions databases, and it would help us to detect and identify the location and time onset of significant methane releases or emergence of new sources of anthropogenic emissions. The third area is regulation. The report recommends that we equip the federal and state regulatory agencies with appropriate methane measurement capabilities. This includes access to relevant data from space-based monitoring and implementation of airborne and ground-based tools, enabling a 24/7 monitoring of methane emissions. We need to design a regulatory structure for a high-speed and cost-effective approach to methane emission reduction from oil and gas operations. That is to identify a, quote, acceptable, end quote, leak level, and just go after, as you saw from Ian's comments, the few but important super emitters. The final goal would be literally a federal roadmap that would bring fugitive emissions down to levels that are negligible for climate change, health, and safety. So it's both a technical and a regulation issue, policy issue that we need to address.
Thanks for that, Ray. So we just passed the half-hour mark here. So before we move into the Q&A portion of the webinar, I'd like to ask each of our panelists to share your big takeaway that you hope readers gain from viewing this report. So Bill, I'll toss that one to you first.
Thanks so much, Michelle. Yeah, let me come back to the point of, I think baselines are everything. If we want effective regulation, we need to know our starting point. And so it's really critical that we look now at really deeply understanding where methane is coming from, how much is being emitted, and that will serve us as a great foundation for all our efforts, both nationally and internationally, to get our hands around and to reduce the emissions of this very important greenhouse gas. Thank you.
Thanks, Bill. Ian, how about you?
Ian, you're on mute.
Sorry. Yeah, I'd like to include in saying that it's kind of an exciting time, right? Interests do seem to be aligned now that the picture of how these leaks are distributed is coming together, and what we need to think about is scale going forward in terms of really extending the number of sensors out there, the wells that are monitored, and to stomp on this problem as quickly as effectively as we can.
Thanks, Ian. And Ray, can you close us out here with your big takeaway?
Well, I think what we're talking about is a roadmap for the country. The half-life of methane is about 12 years. However you look at the opportunities we have to reduce global warming, it certainly gives us an opportunity to make a difference, at least within our lifetime.
All right, thanks so much to everyone for sharing your insights. We're going to move now into the Q&A portion of the webinar. So as a reminder for all of our attendees, please use the Q&A feature to submit your questions. Panelists won't be seeing questions that are placed in the chat box. So let me hop on over there. All right, our first question. Could the science and research community find a resolution of methane monitoring framework, methods, standards, integration, et cetera, before or during COP27? And Bill, I see you've raised your hand for that one.
Yeah, thank you. Also, Michelle, there's a prior question from Laura Green that we should come back to. But on this first question with respect to COP27, I applaud the questioner's optimism. That meeting is coming up in November of this year. It's the 7th to 18th November 2022. So I doubt we're going to solve some of the thornier technical issues that we've identified in this report between now and November, but the climate community is acutely aware of the need to move urgently, and I think we should also applaud the fact that there's a great deal of momentum emerging from COP26, again, both nationally and internationally, around the opportunities afforded by rapid regulation of methane. So, and just as a means of putting an optimistic end to my answer, new methane satellites are going up regularly. There was just a report on the BBC about an effort between the US and New Zealand for a new satellite called Methane Sat that's going up next year. So the efforts to create a federated suite of observing systems, both ground and airborne spaced as well as space-based, is really moving rapidly at pace. And I think that will serve us very well going forward. But yeah, I don't think we're going to solve this in the next 6 months. Sorry.
Thanks so much for that, Bill. Any other comments from our other panelists before we jump on to our next question? All right. So we're going to move to that question that Bill pointed out. So this is from Laura Green. Beyond methane, are there plans for more studies that consider the effect of very complex fluids on our environment, which include petroleum, dissolved organic carbon, including runoff from the built planet, and PFAS, forever chemicals? And as a note, at the Mag Lab, we have an ion synchrotron resonance user facility, which is a mass spectroscopy facility that looks at complex fluids with a mass resolution of almost 1 electron. So thoughts on that?
Certainly outside my area of expertise, I think actually that's probably more of a question for the APS.
And Bill?
Yeah, so I think the answer to this question is it sort of depends. The focus of our report was on gases that alter the energy budget of the climate system, and the jargon that's used in the climate community is radiatively active species. There are hundreds of greenhouse gases that we currently monitor. Many of these actually did not exist in nature. So the chlorofluorocarbons and HCFCs were invented in the 1920s as a refrigerant, and quite literally you couldn't have measured them in the Earth's atmosphere before they were invented. those are all being very carefully monitored now. And the National Oceanographic and Atmospheric Administration, for example, has a set of ground-based measurements that they use to measure those species in great detail. The question, though, is really around other fluids that have a variety of adverse environmental consequences. And I'd have to say that that's not an area of my subject domain expertise. So let me turn that question over to Ray.
Well, I would just like to focus on the elephant in the room, and that is right now, about half of the methane emissions into the atmosphere come from the oil and gas sector. But there's the other half as well, namely from agriculture and from waste emissions. One of the ideas behind our study is that these sensors, which of course we're proposing to develop for point sources, could also be used for these more distributed sources. What we're talking about is trying to deal with the total methane emissions that are entering the atmosphere. They're significant. Whether we can do that in a timely basis to reach all of the targets that we've set remains to be seen, but certainly we need to get started to try and deal with this very powerful greenhouse gas.
Thank you so much, Bill and Ray, for those comments. The next question we have is two parts here. So the first part question is, what about large leaks from operators who are out of business? Will you seek, funding to close those? And what else can we physicists do to solve this critical issue? So yeah, I toss that over. Maybe Ray, you'd want to talk about leaks from operators that are out of business? Well,
first of all, the operators now are really enjoying natural gas at $8 a million BTU. It's 4 times what it was not so long ago. And as a consequence, the amount of flaring that we see in Texas has dropped by about half. So there's some rather amusing consequences of the market that's beginning to take place. Also, the industries themselves are well aware of these issues and are starting on their own to reduce emissions. The problem has been that the agencies that are responsible for air quality control, for example, TCEQ in Texas, simply don't have the instruments available to be effective on a statewide basis. And so what we're proposing has implications far beyond a national system. It really comes down to a point of helping the private and state regulators to do their job.
Ian?
Yeah, I guess I would just add to Ray's point a little bit in that the host of technology that will hopefully help the ongoing operations could easily be applied to those other wells as well. In fact, a lot of the decommissioned wells are interspersed among active oil and gas plays, so you end up seeing them either coincidentally. But it's absolutely true. The cost of fixing one of those wells is expensive, and unfortunately that's a public policy question to identify sources of funds to seal up those wells. But it is one.
All right, thanks so much. And I think we got to that second part of, the physicists, we have a lot of technological opportunities there. Does anyone want to elaborate a little bit more on, from the physics side, from the Optica side, what can we do to really push this forward?
Well, Michelle, that was,
Yeah.
if I may, that was part of the motivation for identifying or having a chapter in the report that's really dedicated to the ways in which pushing optical sensing technology, increasing signal to noise in parts of the spectrum where that's hard to do. That was really issued as sort of the, waving the red flag of invitation to the physics and optical communities to dive in on those problems. we need better spectroscopic measurements of methane. We need models of methane that have been ported to supercomputers, because that's an incredibly tough problem to compute at spectrum ab initio from Schrodinger's equation. Doing remote sensing of methane in the infrared is really tough because you're out of Rayleigh scattering. It's 1,000 times weaker than it is in the visible. So it's really hard to sense the photons, and you don't get very many back from the atmosphere. So again, it's another really tough problem. So we identified tough problems where we thought the physics and optical communities could really dig in.
Thanks, Bill. And Ian, you want to add some comments to that?
Yeah, although Bill hit many of the points that I was hoping to make, certainly in terms of the sensing for, terrestrial sensing for oil and gas, we've already kind of hit a tipping point where it's cost beneficial to monitor these systems, but any reduction in cost will really speed up that uptake. And something that Bill hit on a little bit, there is a separate problem. There's the how do you fix the leaking well problem. But the other thing we touched on in the report is that there's how do you construct this global budget? And for that, I just double down on Bill's point that we really need a different set of sensors that are very accurate, very precise. We need to understand the methane databases, because they, even CO2 databases we struggle with from a satellite remote sensing standpoint, and the methane. Our understanding of the methane spectra is quite a bit behind even where we're at with CO2. So there's a lot of room for improvement there.
Yes, thanks so much for that, for those thoughts. Our next question that we have here, are the super emitters oil and gas production fields? What is the nature of these leaks? Is it bad plumbing? Are they always localized? So, thoughts on where these leaks and what they are. Ian, yeah.
Yeah, so the answer is it can be an awful lot of things, and I think we're just starting to understand that. There was some work by the EDF that basically stated that the obvious sources are often not the things that are really creating these leaks. It's where something has really gone wrong. There's some unexpected breaks, some widely malfunctioning equipment seemed to be the implication of that study. Unfortunately, it's not a simple question of just monitoring where you think the leaks might occur, because these are complicated systems, and they can malfunction in a number of ways. And the number of sources of leaks is the ways they can leak is pretty significant. There's not a simple answer to that one. We do need to monitor everything.
Everywhere, all the time. It's a constant challenge. Ray?
Yeah.
I don't want to take too much time, but the amount of flaring has dropped as a consequence of the market, but still represents a very large contribution given the amount of total gas production. And so there's a background level that we also can deal with in trying to reduce methane emissions.
All right.
Michelle, I just wanted to call your attention. There are a couple of questions from Joe Sable that were contributed at 9:30 and 9:34.
Yeah,
At least appear at the top. Yeah.
Okay. Yep. I can scroll through here. So we are trying to consolidate questions.
Oh, gotcha.
Externally. So that's apologies there. We're not going in order of sequence there.
Gotcha.
So we will make sure to, again, try to get to as many of these as possible, and we'll take a look at those. So sorry about that. Let's see. All right, let's go ahead and do one of those questions. So the first one that I'm seeing here is, what if we simply reduced beef consumption by, say, 50% immediately, reducing animal source emissions for methane? Bill?
Right. Well, this is a delicate subject because people love to eat what they like to eat. But this has been examined quite a bit in connection with the recent IPCC assessments. The literature suggests that a vegan diet is 1/3 as carbon as intensive as a animal product heavy diet, and the UN's report on land use change flagged the fact that about 20% of global CO2 equivalent emissions are due to animal husbandry in one form or another. So yes, the use of animal protein, especially from terrestrial animals, is a big problem. And I will, but I'll leave the resolution of that to sociologists and dietitians. That's a tough issue.
Thanks so much for that, Bill. All right, so let's see. The next one that we're gonna turn to a little bit now are technology challenges. So, what are the main hurdles that you project for continuous ground-based sensors to scale to the capacity that we need to make that measurable impact? Are there any ideas on how to mitigate that scaling challenge? Yeah, Ian, go ahead. Yep.
Oh, okay. Sorry. There's not a simple answer to that, partly because there are so many different sensors and they all probably face slightly different scaling challenges. Some degree, the ones selling to market, at least, the ones that I'm familiar with, seem to be scaling as fast as they possibly can. So send them your grad students, I guess, is maybe one answer. But from a regulatory standpoint, kind of incentivizing to try and accelerate this adoption, I think, is also there's a number of ways you can do it. They're probably all worth thinking about. But at the moment, the market seems to have an appetite that's at least equivalent to production capacity in the foreseeable future. So.
Thanks, Ian. And Ray?
Well, what is needed is a inexpensive detection system sufficiently sensitive that it can separate the fugitive methane emissions from, say, oil and gas from the background. And this depends, as Bill has talked about, on the isotopic nature of the carbon that's involved in the methane. And so you're talking about a fairly sophisticated sensor that can distinguish between different carbon isotope concentrations. But it's terribly important because when you are looking at, for example, ground level, there's a background from all those other sources that really complicates the ability to pinpoint where your sources are coming from. So it's not a trivial issue to develop an inexpensive, scalable, sensitivity sufficient sensor that can be used in the field.
Thanks so much for that comment, Ray. So kind of following on from that previous question, how about using these microcontroller-based sensors, right? Arduino, DIY, citizen science types of sensors. This commenter thought that something like SETI or home weather stations would help us get in the right direction. So thoughts on those low-cost sensors? Ian?
I guess I can comment on them a little bit. Yeah, in fact, some of the companies that are instrumenting these oil and gas wells, that's very much what their sensors look like. They're an array of these small but somewhat drifty sensors. But if you put enough of them around, the drift doesn't really matter because you can intercompare them, and one of them will almost certainly see a very strong enhancement from a plume that comes through it. So there certainly is a commercial solution there. In terms of a private citizen effort, that's maybe a little tougher to envision exactly how that would work. And the other thing is these sensors to really be effective, you need to monitor an awful lot of sites, right? It's sort of approximately the 1 in 1,000 type leak. Or if you look at 1,000 pieces of equipment, you'll see one leak that's really in this category of large. So it's interesting to think about. I think in terms of monitoring CO2 or methane in urban environments, there's some headway to be made there. For the oil and gas, I don't quite have a picture of how it fits together.
Thanks for those thoughts, Ian. This next one wades more into maybe a regulatory arena. So is methane classified by the EPA as a pollutant? What about imposing a carbon tax on methane emissions? Generally, big businesses respond to loss of revenue, like taxes. Bill?
Thank you, Michelle. So the regulation of methane has been on a little bit of a pendulum. In 2016, the Obama administration, through EPA, proposed a new source rule known as an APS rule regarding methane emissions from new modified and reconstructed facilities in the oil and natural gas sector. So this would have brought methane under their regulatory umbrella. That was rescinded during the subsequent administration in 2020. In 2021, Congress came back with a Congressional Review Act resolution that found that that rescission had not followed appropriate federal rulemaking procedures. So they disproved the rescission and reinstated the 2016 NSPS for new facilities and opening the door to new regulation. And that's currently where things stand. So there's also an executive order from EPA to promulgate new methane regulations. So there is movement there. I think I'm going to sidestep the second question with regards to the idea of a methane tax, if I may.
Thanks, Bill. Ian?
Yeah, I would just double down on Bill's point a little bit, and that it is very difficult to effectively regulate something that you can't measure. And at this point, we don't have an idea of that full methane budget and where everything is coming from. If there were some sort of a national network installed, then regulation would be much more feasible to implement in a way that couldn't easily be sidestepped or be a little bit arbitrary and capricious. But there's a technology piece that still needs to be scaled up before you can really talk reasonably about that sort of thing, I think.
Thanks, Ian. And we have about 4 minutes left here, so this may be the last question. We'll see how we go. So this one starts looking at kind of the international picture here. So physics principles do not depend on geography, but practical deployment of the sensors does. So the question is, are the new monitoring techniques equally effective in the far northern latitudes like the Arctic? And how is international cooperation in methane monitoring, and R&D all related? So I see both Ian and Bill here. Ian, you're on my screen right now, so we'll go with you.
Okay, sounds good. Yeah, so the nice thing is that there are a wealth of monitoring technologies out there, and they all seem to have different constraints. I only know of a few cases where people are monitoring in the Arctic, but it seems to be doable. One of the bigger challenges is trees. A lot of these sensors incorporate a meteorological model. That's very easy in the West where things are wide open, but as you get into Louisiana or the Marcellus Basin, things get a lot more constrained, and that does require different technology.
Perfect, thanks. Bill?
Yeah, just point out that this is one of the reasons why we're calling for a federated approach. So we have eyes in the sky, satellites that can, with their orbital configurations, see every part of the planet, basically every day. Now, depending on the nature of the sensor, the return time to any given geographic location may be up to 2 weeks. But basically, we can see everything from space. And the primary challenge there is if you need sunlight, then there are times of year where either the North or the South Pole may be a little challenging because you're looking down at the poles during a period of time when there's the orbit is not favoring you. But basically, the satellites provide a means of, as the questioner asked, sort of ignoring geographic boundaries and national boundaries.
Thanks so much, Bill. And Ray?
I think you're talking about a very difficult issue. If you look, for example, at what we have been able to measure, namely flaring from satellites, the United States is about fourth in line. You're talking about Nigeria, you're talking about Russia, which is the worst offender. We can come up with limits and we can talk about how bad their attitudes may be, but to enforce them to follow, for example, the rigor that the United States might instigate is quite another matter. And so I'm afraid our little panel is not prepared to deal with a global issue like that, but very few are. This is really a United Nations issue. And even then, I'm not sure that it will be effective on a global scale.
Thanks so much, Ray. So we are running out of time here. We weren't able to get to all of your questions, but there'll be an email coming in through the chat if you'd like to reach out to Nico, who is our fearless leader in this panel. So I want to close out by thanking all of our panelists today for sharing your time with us, and of course, everyone in the audience for really taking the time to engage on this important topic. Please do reach out to Nico at that email he's sharing in the chat. And otherwise, thank you all for joining us and have a great rest of your day.